So now we'll look at those special cases where you have a stationary point and it's also something that isn't a maximum or a minimum. It's called a stationary point of inflection. Inflection in calculus is talking about how a curve is shaped. Generally speaking, if we look at an x cubed graph, because it has a stationary point of inflection, that's not quite enough of a bend in there. It's got to come right flat there. That's more realistic. It's got a good flat point in there. In calculus, we talk about how a curve goes. We've talked about things going increasing and decreasing. Another thing that describes a curve is its concavity, how it bends. And if I take this x cubed graph, and if I say I have a stationary point of inflection there, what happens at a point of inflection is that your graph changes concavity. So if I color code this part of the graph is all curved down like this. And we would say that part is concave down. After that inflection point, this part of the graph is all curved up, and we would say that's concave up. Where it changes from concave down to concave up, we have an inflection point. And if your inflection point also happens to be a place where your tangent is 0, we call it a stationary point of inflection, because it's an inflection point and a stationary point at the same time. So what you have to have for this to happen is, first of all, the derivative has to be 0. That's the way we get a stationary point. And then if we looked at the place where we have our stationary point, we notice that when you plug things into your derivative, that it's increasing before and increasing afterwards. So we would have the slope, or the derivative, has the same side, either both increasing or both decreasing. And an interesting thing happens wherever you have an inflection point, the second derivative will be equal to 0. So the second derivative at that point will also be equal to 0. So we're going to do a couple of graphs, find all the stationary points, say whether they're maximums, minimums, or inflection points, and then graph it. So I'll give you a head start on them. Here's the first one. Start with our derivative, 3x squared plus 6x. Can you imagine still having to go to the definition of the derivative for each of these as part of it? That would be a little painful, wouldn't it? So there we go. We make that equal to 0. And this can be factored. You can take out a 3x, leaving you with x plus 2. And so x could equal 0, or x could equal negative 2, are the two places where your derivative is equal to 0. So if we draw our number line and put negative 2 on there and 0 on there, we have 3 sections we have to check. Now when we're checking whether our function's increasing or decreasing, we're always plugging back into the derivative. So something less than negative 2. Now you could plug it in the derivative right there at the top. I also find that it's really helpful if you factored it to plug it in there, because you can do a little bit of mental math with positives and negatives a little bit quicker. For example, if I choose a negative number like negative 10, I can tell right away that this is going to be negative, because negative 3 times negative 10 would be negative, and this will be negative. And negative times a negative will be positive. So I know this section is positive, and we're increasing here. If I try a number between negative 2 and 0, like negative 1, this first part is still negative, but now this section will be positive. because negative 1 plus 2 is a positive 1. And a negative times a positive is negative, so then I know my function is decreasing. And finally, if you try something bigger than 0, both of those will be positive, and it's increasing again. So from this first derivative test, we know that negative 2 is going to be a local maximum, and at x equals 0, we have a local minimum. So I like to put those points down and label them. This one is our local maximum, and this one is our local minimum. Now to find the y-coordinate that goes with those points, we'd have to plug it back into our original equation, because we're talking about actual points on our actual graph. So if I plug in 0, well, that one's easy. I get 1. If I plug in negative 2, negative 8 plus 12 is 4 plus 1 is 5. So now we also know exactly where those points are. Now when we go to graph this, we can plug in our points. We have 0, 1. We have negative 2, 5. We know that our function is increasing, then decreasing, then increasing again. The only important point that we are unable to figure out right now is that one. Our function does not factor nicely. At least it doesn't appear to factor nicely. We could try the factor theorem to plug in numbers to see if anything would work, but all the nice numbers with our factor theorem do not work. If you wanted to find that x-intercept, you could use your calculator right now to find out where the x-intercept is. There's also complicated formulas for x-cubed functions that we're not going to get into, because you'd have to use your calculator just as much to figure those out. But we've got a pretty detailed graph. We know where our maximum is, we know where our minimum is, and compared to what you learned in grade 12 pre-calculus for this, the only thing you would have learned in grade 12 pre-calculus that would help you with this graph is you could easily find the y-intercept at 0, 1. And you know it's a positive x cubed graph, which starts here, it might have something in there and go up forever. So the best you could do from grade 12 is estimate, but you wouldn't know what's happening other than it goes through 0, 1. We now, with calculus, find these maximum and minimum values, and our graph is that much more accurate. Okay, try the next one.